My name is Hannah, and I am a PhD student here at the University of Cambridge, and I am studying, privileged to be able to spend my days thinking about some of the biggest unanswered questions in the universe. And I'm super excited to be here tonight to be able to share some of those explorations into the unknown with all of you at home. So tonight we are going to be looking at one of the biggest mysteries of the universe, and it's something which scientists around the world are racing to try and solve. So hopefully it should be a bit of a whistle-stop tour into the unknown, and hopefully something that you will enjoy finding out more about. So to start off our exploration tonight, I would like you all to join me in a bit of a thought experiment. And what I'd like you to do is just take a look around you and take a note of what you can see. So my boring room, I can see, wardrobe, I can see a wall. Now, everything that I can see has interacted with the light, which has then entered my eyes. Okay, so we had light from the lamp, which has hit the walls, and it's then reflected and entered my eyes. And that's what's allowing me to observe it. Now, it turns out that 85% of matter in the universe doesn't have this property. Okay, it can't interact with light, so it can't reflect it, can't absorb it, it can't emit it. So in all intents and purposes, it is invisible. Okay, so I just want you to hold this idea in your head that you, me, everything you've ever seen, so every star, every galaxy, if you've ever been lucky enough to see a galaxy, depending on the light pollution in your area, but everything you've ever seen makes up just a tiny fraction of the mass in the universe. And the rest of it, that other 85%, is what we call dark matter. And not only can we not see this dark matter, but we can't touch it, we can't taste it, we can't smell it. And we will never, ever be able to touch it, taste it, smell it, or see it. Okay, so it's not just that it's too far away. It's actually physically that this stuff, even if it was right in front of your nose, you would not be able to touch it, taste it, see it, smell it. Okay. In fact, there's probably some of it in the room with you watching this lecture right now. So I tend to like to think of this as a little bit like having Harry Potter sitting in his invisibility cloak in the room with me. So he might be there. He's something that's physical. He's got mass, but I can't see him. And I will never be able to see him, provided that he keeps his invisibility cloak on. So you're probably thinking, well, okay, so you said that 85% of the universe we can't see. Well, what on earth is that 85%? Because everything that we know of is built, you're probably used to your teachers at school telling you, matter is built from atoms. Now, okay, I can see atoms, right? I can see the wall, I can see the table, I can see things that are built from atoms. So what on earth is this dark matter? It can't be built from atoms because otherwise I'd be able to see it. And this is the question which scientists around the world are really scratching their heads to try and find out, what is this dark matter? And it turns out that actually on a fundamental level, on a particle level, we actually have no idea what dark matter is. And I think that's something which is hugely exciting, that we've got such a huge part of our universe that we just don't know about. And if you think of all the discoveries that have been made over the last, since humans have been around, we know so much about, very minute things. We can, there are very clever people out there that can work out, they were able to make a COVID vaccine, right? I think that's pretty amazing. But 85% of matter out there, we just have absolutely no clue what it is. And I think that's something which is really quite amazing, and something which is really exciting. So hopefully you're also excited by this concept. And today we are going to explore this idea a little bit more. So before we kick off our journey into the dark world, we are going to just have a little pause and think about our known universe. So this is everything that we can see, everything that we do know. And basically, you can think of the aim of physics as being able to describe the world around us in terms of maths. Okay, so that's kind of our idea of physics. We want to come up with a theory which describes the world around us. Now, if it describes the world around us, it needs to be based on observations or based on things that we've seen, that we've observed in our universe. Now, it turns out in the universe, we have observed that there are 4 forces. So you may have heard of lots of different forces when you're at school. People probably talked about friction, buoyancy, things like that. But it turns out that, again, on a very, very fundamental level, all the forces that you've ever heard of can be attributed to one of 4 fundamental types. Now, these are the electromagnetic force, the strong force, the weak force, and gravity. And as scientists, well, scientists have been coming up with theories which describe these forces, okay? And there's a theory that describes gravity. It's known as Einstein's theory of general relativity, which you may well have heard of. So that's the theory that we have that describes gravity. And we also have a theory which describes the other 3 forces. And it describes, it's called the Standard Model of particle physics. And basically what it tells us is it predicts all of the particles, all of the known fundamental particles in the universe, and it predicts how they interact with these 3 forces. So this is a picture of the Standard Model here. We have the orange and the green particles, which are known as matter particles. So these are all the matter in the universe. And we have these blue particles, which are known as force bosons, or they basically mediate the force between particles. So it's the interaction between matter particles and force particles that give the impression of what we observe as a force. And every different force has its own force carrying particle. So, for example, the gluon is the force particle for the strong force. The photon, which you can think of as being like a unit of light, that's actually the force carrying particle for the electromagnetic force. So if we say that things interact with light, another way of saying that is just that things interact via the electromagnetic force, okay? So when we see, when we touch, when we taste, when we feel friction, they're all actually just facets of this electromagnetic force. So they're all actually to do with interactions between electromagnetic radiation. Now, it turns out that if you have some particle, some fundamental particle, whether or not it can interact with a certain force depends on the properties of that particle. So you can kind of think of each force as having its own password, and only particles that have the right password are able to interact with that force. If they don't have the right password, then they're unable to interact via that force. So it turns out that the password for the electromagnetic force is having electrical charge. So only things that have electrical charge are able to interact with the electromagnetic force, i.e. with electromagnetic radiation. So only things that have electric charge are able to interact with light. We also have the strong force and the weak force, and these guys require the particles to have strong charge and weak charge. And then we have gravity. Now, remember, gravity isn't in our standard model. That's something which scientists would like to include in the future. They'd like to have a bigger theory, like a kind of more complete standard model that included gravity. They haven't managed to do that yet, so that's another problem, but something that a story we'll have to leave for another day, I think. But anyway, it turns out if you want to interact with gravity, then your particle needs to have mass. So gravity is a force, it's an attractive force which affects anything which has mass. So you're probably sitting there and thinking, okay, Hannah, right, so you've told me that you've told us that the building blocks of the universe are atoms, but my teacher in school told me that atoms were neutral. But how can we see atoms if they're neutral? Now, the reason for that is because atoms, on a more fundamental level, are actually built up from smaller particles. So atoms are composed of electrons. Now, electrons are fundamental particles. They exist in our standard model. And atoms are also built from protons and neutrons. Now, you may be thinking, okay, well, I still can't see a proton and neutron in our chart. So where did these guys come from? So the protons and the neutrons are actually built from these objects called quarks, okay, or quarks, and they have quite nice names. They have up, charm, top, down, strange, and bottom. In fact, the bottom quark used to just be called the beauty quark, which I think is perhaps a nicer name. But anyway, it's called bottom now. So we have these quarks, and they actually come together to form protons and neutrons. And this is all predicted by the standard model. So when things come together to form a larger structure, that's all just to do with its interaction. So again, this is all entirely predicted by our standard model. So why can we see atoms? Well, the reason we can see atoms is because although atoms themselves are neutral, they're made up of things which have charge. So we have electrons in our atoms, and electrons have negative charge. So because these electrons have negative charge, the electrons in our atoms are able to interact with light, and that's what allows us to see it. So using this idea of there being 4 fundamental forces in the universe and a set of particles that interact via these forces, that allows us to define what on earth I mean by dark matter. Now, as you'll see again, actually later in the talk, physicists are pretty bad at naming things, and they tend to just name things by like what it says on the tin, okay? So the words dark matter literally quite just mean that. So the word dark, well, what does dark mean? Well, dark means it can't interact with light. So on a fundamental level, we're just talking about something which is unable to interact with this electromagnetic force. And of course, if it's unable to interact with the electromagnetic force, that just means it doesn't have electric charge. So it must be a neutral, fundamentally neutral type of particle. It can't be built from anything that contains electric charges. And the other word is matter. Well, what does matter mean? Well, matter just means something has mass. It's heavy, okay? And remember that everything with mass interacts with gravity. So physicists pretty much use the word dark matter just to describe anything which is able to interact via gravity, but isn't able to interact with the electromagnetic force. And as to whether it interacts with the weak or the strong, nobody knows. So that's an open possibility. But dark matter is just anything which we know does not interact with the electric charge, but it is able to interact with gravity. Okay, so at this point, you're probably thinking, okay, Hannah, right, so you said that there's all this stuff out there. It counts for 85% of stuff in the universe. But if you can't see it, you can't taste it, touch it, feel it, smell it, how do we know it's there? And that is a very, very, very good question. So let's go back to thinking how we know that, you know, the table's here, right? I know the table's here because I can see it, okay? How can I see it? I can see it because it's interacted with light, okay? So another way of thinking about interaction is force, okay? So the table is exerting a force on the light. That's how I'm able to see it. Okay, so dark matter's out there. We know that it can't interact with the electromagnetic force, so it's never going to be able to affect things by the electromagnetic force. But what force do I know that it can interact with? I know that dark matter has mass, and that means it can affect stuff gravitationally. Okay, so the way that we've inferred the presence of dark matter is actually by looking for how it affects things that we can see. So how it imposes a force, how it produces a force, how it affects things that we can see. And we're going to go and have a look at some of the reasons that we can see dark matter now. That we know dark matter exists, or we think dark matter exists now. So there's various different pieces of evidence for dark matter. And we're going to explore some of these in a little bit more detail. Okay, so the whole reason people started thinking about dark matter, or started assuming that there was dark matter in the first place, was because they were making observations of the universe, and those observations of the universe didn't seem to match up with their current theories. And dark matter was like the missing piece of the puzzle that they then inferred to try and make their theories consistent with the universe around us. Now, some of the first kind of evidence that's used for dark matter comes from looking at spiral galaxies. So I've got a picture of a spiral galaxy here. This is the Andromeda galaxy. So what is a galaxy? Well, a galaxy is just a collection of stars. So in the center of our galaxy, we have where most of the stars are. And then we have other stars which are further out in the spiral arms. And it turns out that the stars that are in the spiral arms are actually in orbit around the center of that galaxy. So you can kind of think, okay, well, a galaxy kind of looks a little bit like our solar system. What do we have in our solar system? We have something very massive at the center. We have the sun. And then we have planets which are in orbit around it. So if you were to look at an image of this galaxy, what do we see? Well, we see that most of the light, so most of the luminous matter, is concentrated in the center of the galaxy. So we can kind of think of the center of this galaxy, some people call it the core of the galaxy, as being a little bit like our sun, okay? And the other stars, which are in the spiral arms, are rotating about the center, and due to the gravity of the core, okay? And we can go back to our theories of, remember, we have a theory for gravity. And in fact, in this sort of situation, we can use Newton's laws of gravitation, okay? And Newton's laws tell me that if something is orbiting around a mass which is concentrated in the center, then as you get further and further and further and further away from the center of that galaxy, your speed should be slower. So this is a little bit like what's going on in our solar system. So the planets that are further out, okay, so Jupiter, Venus, Venus is in the center, obviously Jupiter, Uranus, Neptune. The further you go out, the slower the particle, the planet is actually moving around the sun. And that's because the force of gravity, the distance between the planet and the sun is obviously greater, so the force of gravity is less. So we predict the speed of rotation to basically decrease as the distance increases. So when people looked at this situation, they thought, okay, well, right then. So we've got a similar situation, or we think what we've got is a similar situation to our solar system, where we've got things on the outside being attracted to things on the inside. So we should expect that if we measure the speed that stars are rotating at, we expect that it should decrease. Okay, so we expect that the stars that are further out from the center should be moving slower. And Vera Rubin was an amazing astronomer, and she went away and she took a load of measurements. She was able to measure using something known as spectroscopy. She was able to measure the speeds that stars were orbiting at in this Andromeda galaxy. And what did she find? Well, she found this. She found this green line on this graph here. So she found that actually the further you go out, the speed of the stars is staying constant. So we call this a flat rotation curve. But if I look at a specific distance from the core, I can actually see that my star is moving much, 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 much faster than I would expect given given our theory of gravity, okay? So this is telling me something. This is telling me that either my theory of gravity must be wrong, or it's telling me that there must be something there that's making the mass bigger such that the velocity is bigger. There must be some kind of mass there which is there holding my galaxy together. So in fact, what we're inferring from the fact that things are moving much faster than expected is that there must be some kind of mass there that we can't see. Okay, so we know how much, we can make an estimation of how much mass is contained in things like stars from the amount of light they give out. But we're seeing here that there's something that we can't see. And in addition, I can tell that this stuff can't be concentrated in the center. Because if it was concentrated in the center, however much of it there was, you'd still expect to see this decreasing pattern as you went further out. But we don't. We see a flat rotation curve. So this is suggesting to me that there must be some kind of stuff out there which isn't concentrated in the center and that we can't see. So that's our first piece of evidence. There's more evidence to come, okay? And some of this comes from Einstein's theory of general relativity. Einstein's theory of general relativity tells us that mass actually distorts space. So I tend to think of this as like if you've got like a cannonball or a football or something and you put it on the middle of a trampoline, that trampoline is going to bend around the football. And it turns out space is pretty much the same. So if you've got space and you've got space-time itself and you put something heavy in it, so I'm talking like a galaxy, it turns out that space actually bends around that galaxy. And what does that mean? Well, it means that light traveling close to that galaxy can't travel in a straight line. It has to travel around the galaxy, as it were. So because space itself is curved. So I want you to imagine that you are an astronomer and you are looking at a very, very distant galaxy, which I'm going to call a quasar. So a quasar is just a very distant galaxy. And you're trying to observe it. But unfortunately for you, in the way, there is some other galaxy or some other galaxy cluster. Now, it turns out that this galaxy cluster that's in the way is acting a bit like a lens. So what it's doing is it's bending space, and that means that the light that's coming to you from this distant galaxy, this quasar, is being bent around it. So when it comes to you, it's being bent. And this is in a similar way to those of you that wear glasses. You know that light is bent by your glasses. Or we say it's a lens, right? You have a lens which causes the light to bend or change direction. So when you're looking at something distant and there's some mass in the way, what you will see will actually be distorted. You won't see the true image. So if you look at this lower image here, you can see these kind of like arcs. And now what these arcs are actually galaxies. They're galaxies which I'm looking at. But they've been distorted. They should be sort of circular or elliptical in shape, but they've been stretched out into these kind of arcs. And that's because there's some kind of mass between me and it. Now, Einstein's theory, you can make a prediction of exactly, if you measure the amount of distortion you see, you know what it should look like. You can measure the amount of distortion. It turns out that you can then use that to infer the amount of mass that's in the lens, the amount of mass that's between you and what you're looking at. And when people went away and did this, they found that the mass that they were predicting from their measurements was so much higher than the amount of visible mass that was in between them. So again, this is giving us really clear evidence that there is some kind of matter out there that we are unable to see, something which is causing light to be bent more than expected. So at this point, hang on, my slide is not changing. There we go. At this point, we've got various conclusions. So as a scientist, you always need to consider all possible conclusions. So we've either got that our theories of gravity are wrong, or there could be that there's additional particles out there, but maybe those particles are just built from atoms. Maybe it's just they're things like asteroids or rocks or things that are too far away for us to see. So that's one possibility. But there's actually another possibility. And that other possibility is slightly more exotic, slightly more exciting. And it's the idea that the matter that's out there that we can't see is actually something which is not built from atoms. So we call things that are built from atoms baryonic, which just means it's built from protons and neutrons. Things that are not built from atoms we call non-baryonic. And the reason we can't see this, perhaps, is because it physically cannot interact with light. So at the moment, we've got three conclusions. And from the evidence we've considered so far, we're not sure which one is correct. But fortunately from us, there have been lots more pieces of evidence to come. And one of the kind of really crucial bits of evidence that gives us some more insight into what dark matter is known as the bullet cluster. So the bullet cluster is actually a cluster of it's two clusters of galaxies which have merged together. Okay, so you have a group of galaxies and another group of galaxies, and they've kind of merged together. Now, astronomers are very clever, and they can do various different things. So one thing they can do is they can observe this cluster of galaxies in X-ray. Okay, so X-ray is just a type of electromagnetic radiation. And it turns out that as you're forcing these two galaxies to collide, anything that's baryonic, anything that's built from atoms is interacting strongly. It's experiencing a lot of friction, and it's giving out this high energy emission. So it turns out what you can see in pink here, this is just where we've got X-ray emission from the galaxy. And that X-ray emission is basically telling me the location of our baryonic matter. So the pink is the location of our baryonic matter. But we've got our famous trick of gravitational lensing, and we can also try and measure the mass of this cluster or we can measure the location of matter by using gravitational lensing. So again, what I'm doing is I'm looking at these background objects, these background very bright quasars and things, and I'm looking at the amount of distortion and using that to tell me what the location of mass in the lens is. And the location of the mass in the lens, i.e. the total matter, is this blue stuff. So we can clearly see here that the baryonic matter does not coincide with the total matter of this cluster. So this is really clearly telling me that dark matter must be something which is non-baryonic. Because if it was non-baryonic, if it was baryonic, the pink and the blue would be the same thing, right? So all matter would be giving off these X-rays. But we can see there's matter which is not giving off X-rays. So it must be some kind of matter which is non-baryonic. And this is one of the really crucial pieces of evidence that actually dark matter is unbaryonic. Okay, so to just briefly cover, before we briefly cover the next pieces of evidence, which I think are quite interesting, we just need to think a little bit about what the universe was doing in the early universe. So in the early universe, you can kind of think of the early universe as being like a big hot soup. And we had lots and lots of charged particles floating about because the temperature of the universe was so hot that all particles were ionized, all atoms were ionized. And so all of these charged particles, well, what do charged particles do? They interact with light. So we've got lots of radiation and we've got loads of charged particles and they're interacting. So every time you try and have some light try to flow, that light is going to be colliding with electrons and things. And that's going to make the path that the light's traveling in very kind of random. And it means that light will be unable to travel in straight lines. And it also means that your matter can't come together and form large structures. So if you imagine trying to join two atoms together to form something, or eventually trying to form a galaxy or something, it turns out that there is no way that can happen in this very early universe when everything is ionized, because every time things try and come together, a naughty photon, a naughty bit of electromagnetic radiation comes and blasts these atoms back apart again. So normal matter in the early universe, in this very early universe when things were ionized, was unable to come together and form structures. However, what would happen if you had some kind of dark matter, some kind of something which wasn't baryonic? Well, if that was unable to interact with photons, then that presumably would be able to start clustering and clumping and come together. So I just want you to hold that thought in your mind. But anyway, so we know that we do see structures built from baryonic matter, because obviously that's you and I, etc. So we know that matter must be able to start clustering at some point. And it turns out that it can start clustering at this point here, this dashed line. So it's sometimes called recoupling, or recombination even. And it's basically the point where the universe was cool enough for atoms to become neutral. So the electrons, those pesky electrons, could combine with our nuclei, and suddenly we've got things which are much less charges flying about. And at this point, the baryonic matter can cluster. Now, it turns out, if you look at all of the complex structures that we see in our universe today, things like galaxy clusters, in fact, the fact that you and I exist, we all exist because atoms have come together. But cosmologists are very, very clever, and they can kind of predict how long it would take for atoms to come together based on this scenario. And they've managed to tell that there's nowhere near enough time from the time when the universe became neutral to the present for baryonic matter to form the structures that we see today. So this is giving us a very, very clear evidence that there must be something else in the universe that was able to start clustering before the universe became neutral, i.e. something that was unable to interact with photons. So again, this is really clearly indicating that there must be something which is non-baryonic out there. Okay, so I think that's enough evidence for today. So just to update our conclusions, we've now kind of come to the conclusion that dark matter exists, and it must be something which is non-baryonic. It's something which is not built from protons and neutrons. And what we want to now go and do is try and find out what that could be. So your first thought might be, okay, well, it's not built from protons and neutrons, but protons and neutrons are just built from quarks. So could it be that there are other particles in the standard model that could be dark matter? Could it be that dark matter is already some kind of known particle? And it turns out that if you consider all the different possibilities, so again, you could consider things like asteroids, brown dwarfs. It turns out they're fundamentally baryonic, so we can exclude that conclusion. Now, it turns out the only kind of non-baryonic, non-neutral particle that exists in the standard model, so the only kind of neutral, non-baryonic particle that we know of, is something known as a neutrino. So neutrinos have various properties that we know dark matter has. They're massive, they're not visible, they're non-baryonic. However, neutrinos, not only are there not enough of them for us to account for them to account for the extra gravity, but neutrinos are also something which are hot. Now, what I mean by hot is that I mean they're moving very, very, very quickly at the time when I needed structures to be forming. And if things are moving very, very quickly, they're less likely to be able to come together. So these neutrinos are actually moving too fast to be able to cluster in that early universe, even though they're non-baryonic, even though they can't interact with light. So actually neutrinos fail on that front. So we know that neutrinos can't be dark matter. So we've managed to exclude everything from the standard model. And we can therefore come to the conclusion that whatever dark matter is some kind of exotic new particle. So dark matter must have a building block which is not atoms. And this is what we're trying to uncover now. What exactly is this exotic new particle? So as physicists, I tend to think we're a little bit like crime scene investigators. What we do is we take the evidence that we can see and we use it to reconstruct whatever it is that's caused what we can see. Okay, so we come up with a theory which is able to explain our observations. And physicists have come up with various different theories for what dark matter could be, and I'm just going to introduce you to some of the main ones now. So the first one, and this is really the Beyonce of dark matter candidates, it's really the most popular idea of what dark matter could be, is known as the WIMP. And again, physicists are pretty bad with their naming. So they've gone for weakly interactive massive particle. I shouldn't say badly naming, actually. It's a very good name because it basically does what it says on the tin. However, it's pretty unimaginative. So weakly interacting massive particle just means some kind of particle which is massive and is able to interact via the weak force. Now, necessarily, these WIMPs can't interact with light, so that means they're electrically neutral. And in order to be able to explain how structures formed, we also need them to be slowly moving. So that's what we mean by a WIMP. It's just any kind of massive particle which is able to interact via the weak force. Okay, so this is interesting because if WIMPs can interact via the weak force, there are also particles that we can see that can interact with the weak force. So, for example, things like electrons. So these WIMPs should be able to have an effect on matter that we can see. Okay, so hold the idea in your head because we're going to come back to that in a moment. There's also one other very popular candidate, which is becoming more popular actually, which is, in contrast to the WIMP, it's very, 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 very light. So we're talking billions of times lighter than electrons. But once again, it doesn't interact with light, and it doesn't have electric charge, and that's known as the axion. And axions have a very interesting property that if you put them in very strong magnetic fields, they can actually convert to light. But anyway, most of these searches that have been done for dark matter have been done for the WIMP. So that is what we are going to focus on today. So, okay, so we've got this hypothesis, and our hypothesis is that dark matter is a WIMP. How on earth can we go and test that? Well, it turns out there are 3 ways that scientists around the globe are searching for these WIMPs. And I like to think of them as shake it, break it, and make it. So that's the way I remember it. So to start off, let's go for shake it. So the posh name for shake it is direct detection. So essentially what I do here is I'm exploiting the fact that if WIMPs exist, WIMPs we know are able to interact via the weak force, we would therefore expect them on some level to be able to affect visible matter via exerting a weak force on this visible matter. So this method, what it basically does is they have these massive detectors filled with heavy atoms. And the idea is these detectors basically detect what you'd expect to happen is that the dark matter, the WIMP comes in, the WIMP hits the atom, and it causes it to recoil. So it's a bit like if you've ever played snooker or billiard balls. If you have something hit something, then they both end up moving. So the idea is that we're basically looking for atoms that seem to start recoiling without being hit, okay? Now, this is very, very, very difficult to do. The reason it's difficult to do is because there are other things which could also hit our atoms and cause a signal in our detector that aren't dark matter. So things like neutrinos or cosmic rays. So when people are doing these experiments, they actually have to do them very, 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 very far underground. So a couple of kilometers underground, they have these massive detectors. And essentially what they're doing is the reason they're underground is to try and shield it from radiation, from any kind of background. But what they're trying to do is detect whether they can see these recoils. And there are several of these experiments that have been around. So some examples of them are Lux, Zeppelins, the Xenon 1 ton. And basically, essentially, they're all doing the same thing. They're trying to look for these recoils when WIMPs are hitting normal matter. So that was shake it, because the dark matter is shaking the normal matter. The next one we can talk about is break it. So this is the idea that if you've got some kind of dark matter out there, some kind of WIMP, these WIMPs, dark matter, much in the same way that every normal particle has an antiparticle, WIMPs we'd also expect to have some kind of anti-WIMP. And it is possible that maybe dark matter and anti-dark matter, a WIMP and an anti-WIMP, could come together and annihilate each other and destroy each other. So this is the same way that electrons and anti-electrons, which we call positrons, come together and annihilate each other. And when that happens, it's possible that this annihilation, the mass of the WIMP and the anti-WIMP could just be converted to standard model particles or radiation. So one idea is that if there are WIMPs in the universe and those WIMPs are either annihilating each other, or in fact, maybe these WIMPs are decaying, maybe they're decaying into standard model particles, we would be able to see excess radiation, okay? So the idea, for example, is you can take your telescope and you can look at an area in space. Now, we can make a prediction based on standard astrophysical processes, how much, think like gamma radiation, how much high energy radiation you'd expect to be coming from that region in space based on, for example, the astrophysical processes that are going there. And you can then compare that to the amount that you observe. And if you're seeing an excess, that could be indication that there are some WIMPs in that region of space, either annihilating each other or decaying into this high energy radiation. So we can look for excess gamma rays in this way. And one example of that, an experiment that's doing that, is the Fermi Large Area Telescope, which is looking at the center of the Milky Way galaxy and looking for excess gamma rays there. We can also search for excess cosmic rays. So again, these annihilation processes could actually produce extra cosmic rays. And there's the AMS experiment that's looking for that. And finally, these kind of annihilations or decays could actually produce neutrinos. So again, we can look at areas in space. We can think about the amount of neutrinos we'd expect coming from that region in space, and we can compare it to what we see. And again, there are some experiments that are doing this. So for example, the Antares and the Ice Cube experiment, which are based at the North and South poles, and they're basically measuring the flux of neutrinos, so the amount of neutrinos that are hitting the Earth. So that was Break It. The last one, which I think is quite exciting, is Make It. So this is where we are trying to actually make or produce dark matter directly. So you may well have heard of CERN, or the Large Hadron Collider. What it is basically a huge 27-kilometer track under kind of Geneva and France. And what they are doing is they are accelerating protons. So remember, protons are parts of our atoms. They're accelerating around them around the track and colliding them at really, really, really high energies. And we have various detectors situated around this track. And the detectors are situated at the collision points. And what the detectors do is they basically collect everything that comes out of this collision. So you can imagine you've got two protons, you smash them together at very, very high energies. When they're smashed together, they produce different particles, which then maybe decay or they produce radiation. Now, these detectors can collect all of that. Now, it's a very fundamental idea in physics that if you put energy into something, you should always get the same amount of energy out. So we know what the energy of our protons was before our collision. So we know how much energy we had before. Our detectors are very clever, and they can tell us everything they can detect. They can add up the energy and they can then compare it. But what would happen if there was some sort of dark matter being produced in my collision? Well, if there was some kind of dark matter, remember we said that dark matter is not something that we can detect directly, right? It's not something that we can see, touch, taste, or smell. So it would probably pass straight through our detectors, okay? So this would mean that when you added up all the energy at the end of your collision, you'd end up with what seemed like less energy than you started with. So this is how we're trying to detect energy here. What they're trying to do is look for collisions in this Large Hadron Collider where the energy out is less than the energy in, because that's giving us a good indication that possibly there's something being produced that is unable to interact with our detector. So all these experiments have been going on for some time. So have we discovered anything? Well, to think about that, we need to just think a little bit about what we mean by discovery. So it turns out it's all to do with predictions and testing our predictions. So for any given experiment, you can make a prediction of what you'd expect the result of that experiment to be based on your given theory. And remember, our given theory is that there's no dark matter and there's just the standard model, okay? So you can go away and say, okay, well, the standard model predicts there to be 10, it predicts there to be 10 recoils in this direct detection experiment. But you can go away and you can measure the amount of recoils that you actually see, okay? And if the amount of recoils that you actually see is significantly different and significantly has a deeper meaning here in terms of the statistics and the uncertainty on your measurement, which we won't have time to go into now. But if it is significantly different, if what you measure is significantly different from our standard model theory, that basically tells us that the standard model is not compatible with our experiment. Okay, so the standard model is not capable of explaining our results. And that tells us instantly that there must be some kind of physics out there which is beyond the standard model, okay? So that's if you want to discover dark matter and actually say we've discovered dark matter. Now, unfortunately, nothing to date has been significantly different. And we're going to talk about that in a minute. So we haven't actually discovered dark matter. But what we can do is we can actually use the results of these experiments as like null results. So if you do an experiment, instead of comparing it to the prediction for the standard model, you could compare it to the prediction that you'd expect from a WIMP. So we can go away and we can say, okay, well, if I had a WIMP of this particular mass and a WIMP of this particular interaction strength, I'd expect this many collisions, okay? And again, if that amount of collisions that you'd expect from the WIMP theory is sufficiently different, so it turns out it has to be, it's less big of a difference than for a discovery. But if it is, again, sufficiently different, we can therefore conclude that the WIMP theory is unable to explain our observation, and therefore that WIMP can't exist. So what I'm going to show you now is the results of some direct detection experiments. So there are all these different direct detection experiments. Remember, these are just the big, heavy atom detectors underground. Now, what they've gone away and done, you can kind of think of this as a map, and this is a map of possible WIMPs. So along the bottom axis here, I have the mass of the WIMP. And up the top here, I've got how strongly that WIMP is interacting with normal matter. And I can go away, and for every different point in this map, I can make a prediction for how many, recoils I'd expect at one of these experiments. And I can go away and I can do this test. I can compare my prediction with what I see. And what these lines are showing us are everything above the lines have been excluded. So this is telling me, for example, a WIMP here of this mass and this cross-section, we know doesn't exist. So although I'm unable to say, okay, well, dark matter is a WIMP of this mass and this interaction strength, I am able to say, okay, well, it's not a WIMP of this interaction strength. So you can kind of think the aim of these experiments basically is to get these curves getting lower and lower and lower, so that eventually you either exclude all of it and then you could be able to conclude with certainty that dark matter wasn't a WIMP, or you might be able to, as your experiments get more sensitive, so these lines basically tell us the sensitivity of the experiment. As these lines get lower and lower, we say the sensitivity of the experiment is getting higher and higher and higher. So kind of the aim of experimenters is to build bigger and better experiments that are able to sense more of the space. So what this is showing me here is, for example, the dashed lines are how we expect future sensitivities to differ. So you can see that, for example, this black dashed line here is what we expect super CDMS, which is the new version of super CDMS, how sensitive we expect it to be in the future. So this means that once this experiment has been carried out, either we will have excluded everything above this black line, so we've either excluded this, or if dark matter was in this region, we would have actually been able to detect it, okay? So the solid lines are showing us everything that we've concluded isn't dark matter, but the dotted lines, we're predicting that once these experiments are over, either all of this region would be excluded, or if dark matter was the particle in this region, we would have actually then been able to discover it because this particle is sensitive to this region. So all of these experiments are currently being built at the moment, and it's going to be hugely, hugely exciting to see what happens when they've got all their data. Are we able to exclude all of this space, or will we actually even uncover dark matter? And who knows? It could be these experiments, the experiments are going to be starting very, very imminently. It could well be that dark matter is discovered imminently. Who knows? Now, you're probably thinking, okay, well, these experiments have been around for a while, and we have yet to actually have any positive results. We're yet to say, okay, we've discovered a WIMP. So one possibility and it's something which is becoming an increasingly attractive possibility to scientists, is that dark matter is actually not a WIMP. Perhaps it is something else. So we already talked a little bit about these axions. There are many, many other theories for what dark matter could be, and they all have slightly different properties and slightly different behavior. One of my favorites, which I think I have to tell you about, is this idea of mirror world dark matter. So this is the idea that we had the standard model and we had every particle and we had every force. This is the idea that out there is a kind of dark analogy of every particle. So as well as electrons, we would have a dark electron. As well as a proton, we'd have a dark proton. And we have the same forces as well. So as well as having a weak force, we'd have a dark weak force. Electromagnetic force, we'd have a dark electromagnetic force. And it turns out, or this theory is basically that there's all this matter out there which can only interact through these dark forces. It's unable to interact through the normal weak force, the normal strong force, and normal electromagnetism. So you can have like a whole other world out there that's basically governed by its own forces, but it's unable to interact with our world. So we would never actually be able to detect it. On a particle level. I mean, obviously we could detect its gravitational interactions, but we would never be able to detect it in a detector or anything, because it is fundamentally unable to interact with our forces, so unable to affect particles in this way. So the idea of whole parallel universes maybe are less bizarre than you may well think, based on science fiction movies. And I think, moving on in the future, there are more and more ideas as we exclude more and more of this WIMP space. There are more and more theories being come up with, and there are some hugely exciting and compelling theories being thought of all the time. And it's really our job as scientists, as theoretical physicists, to come up with new theories of what dark matter could be, but not only to come up with those theories, but to think about ways that we could try and test that hypothesis. So any theory that you come up with is only as good as its ability to describe the world around us. So not only do we need to come up with a theory which makes sense, but we need a theory which is able to describe behavior around there, and ideally a theory that we could potentially test in the future. So this is a hugely exciting field, and I would encourage you all to keep your eye out on the news and see if you do hear about any stories, because these experiments are releasing results all the time, and very often there'll be a result which people get very excited about, because, for example, there was a result quite recently at the Xenon 1 ton experiment where they started seeing an excess of recoils, and everyone got hugely excited. They were like, is this going to be dark matter? Is it going to be dark matter? Now, at the moment, they haven't quite got to the level that it's significant enough to be definitely dark matter, because there are other reasons which could explain that excess. So we can't call it a discovery, but there are certainly very, very exciting results to come in the future. And although dark matter is dark, I certainly do think that research for it in the future is looking bright for dark matter. So just to bring our talk to an end, I realise I've talked quite quickly, but hopefully you are now as excited as me about dark matter and what it would mean. So just to conclude, we've got strong evidence that dark matter exists. We need it to explain these observations about our universe, which we can't explain in any other way, that normal gravity is unable to explain without extra mass. Our most likely idea of what dark matter is some kind of exotic particle, something which is beyond the standard model. And scientists around the world are racing to try and pin down the nature and properties, so trying to pin down what the mass and the interaction strength of the dark matter is, by considering the way that this dark matter could interact with visible matter. And this really is an international effort. There is collaborations going on between experimentalists and theorists all across the globe, and it is a hugely exciting area of research, and really is one of the biggest unanswered questions. I mean, the fact that we don't know what 85% of the mass in the universe is it's mind-blowing. And hopefully you, like me, are now really excited about this and what the future might hold for dark matter.